So we're going to be finding the percent composition of C37H64 for problem number 1. So the first thing you want to do is kind of write it like a grocery list. So you want to write C, and then you want to write H, and then you want to put the number for each element. So C is 37 and H is 64. And you want to multiply these by their atomic mass. So you would look at the periodic table, and the atomic mass for carbon is 12.01, and the atomic mass for hydrogen is 1.01. And you multiply these together. So carbon would be 444.37, and hydrogen would be 64.64. And you add these two together, and the total is 509.01 grams of carbon 37, hydrogen 64. And then the next thing you want to do is to find the percentage for carbon. You would take this number 444.37, and you want to divide that by the total. And you would get the amount 0.8730, and that's the same thing for hydrogen. So you write it out. You take this number, 64.64, divided by the total, and that number is 0.1270. And what I do is I move the decimal over 2 spaces. So then you would get, for carbon, 87.30%, and then for hydrogen, 12.70%. And the way to make sure that you're correct is you would add up both of these, and you should get 100%, and that's how you know you're correct. So that's percent composition. We're going to answer the question, how many moles are there in 34.6 grams of carbon hydroxide? So we're answering question number 2. The first thing you want to do is label what you're given. So you're given grams, and you want to find moles, so G and F. The first thing you do is write out what you're given, so 34.6 grams. And then you find the molar mass of this molecule. So that number is 509.01 grams. And then you put what you're looking for at the top, so that's just 1 mole. And you multiply these two together, and you divide by this number, and that gives you 0.068 moles. And that's all you do. That's your final answer.
Okay, so for number 3, I have to find the empirical formula for C37H64. And for the empirical formula, we have to find like the simplest form of this atom, and we can see that 37 is a prime number, so we can't really break that down. So C37H64 is already the empirical formula for this molecule.
Question 4, I'm going to be drawing out our molecule of C37H64, and I'm also going to be stating the geometries and if they are the same. So here we go. And here we go. This is the complete molecule with all 37 carbons and all 64 hydrogens. So next we are going to talk about the geometries of the single carbons within this molecule. And as you can tell, each one has about 4 different molecules going off of it. Each has like a couple hydrogens, carbons, or 2 carbons, hydrogens. for pretty much all of them, even these guys in the middle, they all have 4 molecules. So that means the molecule geometry is a tetrahedral, which means that also that every one is the same. And that's it for question 4.
5, I have to balance the equation with O2. So you can see that C37H64 is a hydrocarbon combined with O2, thus making it a combustion reaction. And first, I'll go ahead and find each. So we see that there are 37 carbons, there are 64 hydrogens, and there are 2 oxygens, and then I have to do the same for this side. There are 1 carbon, 2 hydrogens, and 3 oxygens. And we can see that from looking at this 37 and 1, we can easily make this equivalent. So we can make this 37, thus making this 37. Hydrogen, we can see there's 64 and 2, so if we divide that, we get 32, thus making this 64. And this makes 74 oxygens, also with 32 oxygens, making 106. So we see that 106 oxygens, we see that there's 2 on this side and 106 on that side, making 53 over here to make 106.
Number 6. If you have 34.6 grams of C37H64 and 19.6 grams of oxygen, how much carbon dioxide and water can be produced? So first I have to convert the 34.6 grams of C37H64 to moles, and I need to find the molar mass. So the atomic weight of carbon is 12, so I multiply that by 37, and for hydrogen it's 1, so I'm just gonna go ahead and put 64. So if you add that up, it's 508 grams. So you put the molar mass on the bottom of the dimensional analysis, and you divide and get, so you put 1 mole on top, and that's still just division, and you get 0.0681 moles of 637H64. So then you do the same thing for oxygen. You have 19.6 grams and the molar mass of oxygen is 32. One mole on top, and this equals 0.6152 moles of oxygen. So after this, you have to compare the 2 values and see which one is the smallest, and my molecule is the smallest, which is actually the limiting reagent, because it's going to run out faster because there's less. So I balance equation, and we also use the limiting reagent to find out how much carbon dioxide and water can be produced. So our limiting reagent is C37H64, and the ratio is 1, which is here, 1 mole of C37H64 to 37 moles of carbon dioxide. then you multiply 37 times 0.0681, and this should give you the number of moles that can be made of carbon dioxide. So you can make 2.52 moles of carbon dioxide. I'm gonna do the same thing to find out how much how much water I can make with our limiting reagent. And you still have 1 mole to 32 moles. 1 mole, 32 moles. And we're still using the same limiting reagent. So then you multiply 32 times 0.0681, and this gives you how many moles of water you can produce. And when you multiply them, you get 2.18 moles of water. The question is, which is the limiting reagent? And to actually finish out number 6, you have to find out what the limiting reagent is. So we found out that my molecule, C37H64, is the limiting reagent, which makes oxygen the access molecule. So C37H64 will run out quicker than oxygen.
Okay, now we're going to answer question 8 about how many sigma and pi bonds are in our molecule. So when at closer inspection, you can tell that there are a lot of single bonds. So that means there are no pi bonds, because those are double bonds. So for sigma bonds, I went ahead and counted every single line up, and there are about 106 sigma bonds in our molecule. Now we're going to answer question 9. Are there any polar bonds within our molecule, and are any strong enough to be considered ionic? So from the electronegativity table, we can see that carbon has about 2.5 and hydrogen is 2.1. So when you subtract these out, you get 0.4, which in fact makes it polar. So these two molecules are polar, but between the two carbons, they are not, because it equals out to 0. So they are nonpolar. And are any strong enough to be considered ionic? That would be no. To be ionic, you would have to be 1.7 or higher within the chart.
Okay, so we're going to answer the question, what is the hybridization of the carbon in this molecule? C37H64 for question number 10. So to find out what the hybridization of this entire molecule, first we'll look at a small portion of this molecule. So we're going to draw that out. So C has 2 s orbitals and 3 equal p orbitals, so I'm going to draw that out. So the whole point of hybridization is to combine these. So we want 4 equal places where hydrogen and carbon can bond. So it would be sp3 in those four spaces. So now carbon and hydrogen can bond to carbon. So the answer would be sp3 when you combined all these together. Okay. The way that I knew that there was 4 orbitals is you need to count the adjacent atoms surrounding the central atom. So there's 1, 2, 3, 4. So that's the way that you know that you need to merge 4 orbitals.